It's always hard to follow Clive, and apparently now I need to give a lightning talk. Before I go from the title slide, I just want to mention the list of co-authors there is but a small representation of the Moonrise science team, and I owe them a great debt of gratitude because they seem to be able to come up with unlimitless things one could do with a sample returned from South Pole-Aitken Basin. So it's really a phenomenal group. So there's South Pole-Aitken Basin, so named because it stretches from the South Pole to Aitken Crater on its northern rim. It's huge, it's important. We need to return samples from there at some point. And there's the landing site. Okay, so all kidding aside, it's important not only for lunar science. There are many reasons we want to study South Pole-Aitken Basin and get samples back for lunar science. But one of the motivations for its science priority, especially through the Decadal Survey, is that it also allows us to address some questions of solar system significance. What happened in the first 500 million years of solar system evolution? This is, as has been stated well by previous speakers, uniquely recorded on the moon. So high priority in the Decadal Survey, and I still think it's important to get samples back from this basin. Okay, why is it important? It's a unique location in the solar system. It's huge, it's enormous, one of the largest impact basins in the solar system. As such, when it formed, it produced a huge amount of melt. And that basically resurfaced a huge area and resets the isotopic chronometers of a very, very large area. And so we think that samples from within the basin will record the date of its formation, and as such it will, as the oldest impact basin on the moon, will anchor that impact chronology. So critical science is to get samples back, determine the age of the basin, but perhaps also determine the range of ages as we have for Apollo samples, which we think gives us information about the early basin flux. Okay, so specific questions that we would like to address. What was the heavy bombardment history of the moon? What was its duration? Was there a cataclysm? Whether or not we can uniquely answer the cataclysm question may depend on a number of things, but we won't get into that here. What are the implications for early Earth and terrestrial planets? As Brett pointed out, this is a critical time on Earth. Just the formation of Imbrium Basin would have a huge, huge effect on Earth. What would the formation of a South Pole-Aitken Basin have on Earth? And then again, what are the implications for solar system dynamics? We have a number of really intriguing models ranging from the Nice model, the Grand-Tack model, pebble accretion, and so forth. These are great models. It's time to get some samples back that we can use to test some of these models. Okay, so there's a lot of compelling science that can be done, and I include just a few things here. I won't go through these things in detail, but helping to advance our understanding of the giant basin formation process. There are questions relating to the crust, mantle, and core structure of the moon and its internal evolution that we can address with such samples. And certainly the first basalts from the far side would allow us to test some interesting ideas about the heterogeneity of the far side versus the near side. Okay, so just briefly, let me talk about some key compositional and mineralogical signatures that one sees from orbit. And this perhaps informs where we might wish to go to sample basin materials. So shown on the left and in the center are lunar prospector gamma ray data for iron and thorium. And what you see is that there are enhancements in both of these elements that are clearly associated with an interior part of South Pole-Aitken Basin. That's not the entire basin, but the interior part. And the fact that these compositional signatures persist tells us that there are materials in these regions that relate to the original formation of the basin. So we think this would be, in these areas are the key places to go for sampling South Pole-Aitken Basin impact, melt, and derived materials. We see it also in the mineralogical, here, that's kind of hard to operate. In the mineralogical signature here, Dan Moriarty is going to talk more about that at this workshop, so I won't address that any further, other than to say we also see the signature of the basin in the mineralogical signature from orbit. So with reference to the cross-section at the bottom, This shows kind of an ideal cross-section, but the idea is that many impact basins, large craters, have occurred since the formation of South Pole-Aitken Basin, and they mix materials, and they've created this regolith and even megaregolith that we see and sense today from orbit. But the idea is that toward the center of this basin, one should find the most concentration of materials from the original basin formation. Okay, there are a number of things we could look at, but let me just show the magnetic signatures here. This is also very interesting. You see in the northwest quadrant there, one of the strongest magnetic signatures on the moon. This is very interesting in terms of potential paleomagnetic studies. This relates to some new science that's being done with very high resolution, very high precision techniques for determining the magnetometry of samples that has emerged just in the last few years. So there's been a suggestion that there's evidence for a intense core dynamo between about 4.2 and 3.6 billion years. It would be great to be able to test this. When was this dynamo initiated? What was the source of energy? Did this have to do with core crystallization, with impacts? What was it? So the idea is to get samples back, relate them to the age that we can determine. And by the way, we only have one sample analyzed with these modern techniques that has an age greater than 3.9 billion years. So we really need something in that 4.2 to 4.3 range, or at least very old. Okay, there's another idea that has come up in recent years. Here showing a cartoon drawn by Schultz and Crawford, but David Kring has also talked about this. Potentially a relationship between the formation of South Pole-Aitken Basin and this very interesting area of large fracture system that was identified in the Grail gravity gradient map on the near side. Is there a relationship between these two? It would be great to, we may not know that for sure by getting samples from SPA, but we can at least date SPA's formation and have some idea about this. We can look at the samples, and this is showing a histogram of zircon ages from Grange et al.'s work that shows this interesting peak at 4.32 billion years. Is this perhaps associated with South Pole-Aitken Basin caused magmatism? Because these are samples from the near side now. So ideally what we would like to see with dating SPA materials is, do we see a distribution that looks something like this? Do we see a spike at some specific old age? If it was 4.32, I think that would be very interesting. So the answer is in the samples. I show one particular approach to this problem, which would be to get a sample of regolith back and concentrating on the rock fragments. One might, with Moonrise, we would have concentrated rock fragments by sieving, but those are the key. Those are what we need to determine the ages. Those are what we need to determine compositional relationships and make a relationship between age and impact melt composition and determine what's SPA and what's something that has come after SPA. So getting the samples back, these are large enough to do many different types of analyses on, specifically with some of the developments in recent years in microbeam techniques, from laser argon analysis to shrimp and ion microprobe analyses of uranium and lead. Okay, so selecting a landing site, I'm just going to show one possibility here. Obviously, it's a big basin, and there are approaches that would lead you to go to different locations. I'm going to focus on the interior of the basin here, and just shown on the right is one such area where you might, if you were concerned about finding flat areas and safe areas to land, and you want to be in the interior of the basin, that's a place that you might go to. You'll notice in red there the Constellation Interior site at 60 degrees south. There's a location near Baba Crater there, and one north of that, Bose Alder. These aren't intended to be my suggestions for where you necessarily want to land, but these might be design reference sites where you look and say, okay, what do we need to do to really understand these landing sites and the safety associated with landing in these locations? So again, I want to point out that this is just one approach to sampling and taking a landing site. You could imagine automated sample returns might have one objective in terms of where to go to best sample, and if you're cost constrained, how do you do that? versus an Apollo-style sortie mission. That would be a whole different thing. In one case, you're trying to find a relatively safe landing site, and you don't land near big rocks. In the other case, you probably do want to be close to big rocks. So many different ways to think about this. Let me say just a little bit about the landing site safety analysis, and here I want to kind of segue into the great utility and the importance of the Lunar Reconnaissance Orbiter observations. Shown on the right-hand side is a terrain ruggedness map, and this is shown for a NAC narrow-angle camera pair from LRO, from the camera system, from LROC, and within that are a number of ovals that indicate potential landing ellipses. So we can look at these in detail. Here I show blown up now. You'll see we'll go into greater detail. Blown up is area B. You can see the NAC image. Next to that is the topography. That's the digital terrain map that has been a model that has been derived from the geometric stereo images collected by LROC. And then there's a slope map, and then finally on the right-hand side, a terrain ruggedness map. So we have the data now for a number of sites to do a very safe automated landing. That's the point here, or a human landing. We can select good landing sites. Now here we're blowing up just area B, and so you can see that potential landing ellipse there. And although it's hard for you to see, there are yellow dots in there, and those dots are actually boulders that were counted and cataloged by Ryan Watkins. And there's all of 37 boulders within that, greater than about 1.5 meters in diameter, within that landing ellipse. We can compare this using the Diviner rock abundance maps as well, and this area here, area B, is actually lower in rock abundance than any of the Apollo and Luna landing sites and the Chang'e 3 landing site that are shown there. So we can do this comparison quite well. And here we can even zoom in. Now this is about at the limit of resolution to this little crater on the edge of the ellipse, and you can count the boulders there too. We know that the boulders in this part of the moon are really associated with fresh impact craters. Okay, I just want to, this is going to be difficult for you to see, but I want to point out that although we have narrow angle camera coverage of most of the basin, really it's a high percentage, we only have a very limited suite of geometric stereo images because these are expensive images. They require us to slew the spacecraft. We have to image the same ground surface twice under favorable illumination conditions. So it puts a lot of requirements on the spacecraft, and consequently, we don't have as many for full coverage, but we have a lot of areas now that have been covered, and from these we can derive the digital terrain models. See some of the areas you've heard about before. There's ranging from the areas in the interior of the basin, like the constellation SPA interior, there's the SPA exterior, there's Antoniadi, Schrodinger, and a number of sites in the northern part of the basin. So we have a lot of data now, and good and growing coverage is what I would say. Okay, so let me just put the conclusions up and just say, with respect to sample return science, really the key thing is determining the age of basin formation. We can use that to test models for early impact chronology of the moon and effects on solar system evolution. And then there are a number of objectives that one can address that relate to the early evolution of the moon, possible relationship between SPA formation and igneous activity even on the near side, and testing concepts such as the idea of an early core dynamo and internal structure. There are many possible landing sites. We would say you could go to the center of the basin. You could go to the South Polar regions. And let me emphasize, if we go to the South Pole, and I think we will for resource reasons, getting a sample and collecting it and bringing it back will give us important samples with which to address some of these questions. The transient crater rim of SPA. And then again, in terms of landing site planning and hazard avoidance, we now have very highly accurately co-registered data sets. We have very high resolution imaging at the 0.5 to 1 meter per pixel scale, and this provides all of the essential data we need for landing site safety assessment. So sample returned from SPA would address fundamental questions of early solar system history, giant impacts, and internal evolution of the moon. And the LRO data that we have, and thanks to NASA for supporting LRO so well, provides the essential data for not only landing site safety evaluation, but science evaluation. With that, I thank you and see if you have questions.
Hi. When you're talking about sample return from the surface of the moon, what do you exactly have in mind in terms of priority? Do you like land, take a scoop, and bring it back, or do you want to take travel away from the landing site, take a scoop, or do you want to drill? And in terms of priority, you probably want to have all of that. But in terms of priority, which one would give you the best result?
Clive has been whispering in my ear, and he says to say yes to all of those things. With the particular approach that I have advocated, and again, the point is this is a cost-constrained mission concept sort of idea. One could land and very close to the lander actually dig below the surface. The regolith, we know, contains rock fragments. You can sieve those, sort those, and then bring, that's kind of like high grading the sample, if you will, but also you want to have some of that bulk material. So I think you could do it from a single lander and a sample such as that. Now, again, that's sort of a cost and risk constrained approach. If you could afford to send, enough heavy lift capability to have a rover, you might be able to rove in an area and collect materials. But then now the costs are escalating exponentially. And again, one could have approaches that involve human and astronauts and the wisdom that they bring to the surface exploration as well. But for the low-cost approach, I advocated that getting regolith and sieving it to get the gold.
And how, so you have a lot of data from the surface, from LRO, and et cetera, and how much of a difference does it make to land like, 10 kilometers, or what's the difference between the different landing sites in terms of scientific returns? So the one that you took, if we land 100 kilometers to the left, what difference will that make?
Right, okay, so there are key things to take into consideration. This gets into the geologic detail. You have to look at the distribution of craters and ejecta patterns and the age of craters in a given area to try to understand what would be the mix of materials in the regolith at a given site. The other thing to consider, and I didn't show this in any detail, but the distribution of volcanic materials. We'd love to get volcanic materials in this sample, but if you're really going after South Pole-Aitken Basin impact melt, you may not want to land on a Mare patch. You may want to land on something that looks like regolith that has been contributed to from the ejecta of large impacts. So there are a lot of geologic details like that one needs to take into account, and the geologic map is important.
Okay, thanks.
All right, quick question.
Quick question.
Yeah.
How much sample, mass-wise, would you need to make it worth your while? So in other words, what are you looking at from a design standpoint to send back to get the science that you want to get, at least initially?
Okay, so we've made a case that a kilogram of high-graded material, which would be rock fragment material, would be sufficient. You'd like to have 2 kilograms,
Sure.
but it's in that sort of range.
Okay, great, thanks.